questions? All right, so today we're going to go through some techniques on designing grammars, because you're going to be doing a fair amount of that in the next several weeks. So just as a terminology reminder, so when I have a grammar like this here written up in EBNF, then these things are non-terminals. The things in quotation marks that actually appear at the final output are terminals. And these rules here are sometimes called productions, and I may use that phrase. So let's first of all see how we deal with common situations. Let's say I want to parse array bounds. The array bounds are sequences of numbers in brackets. Now, this would be in a language like Java or C++, where you might need to parse something like that. So I need to somehow get the fact known that I want to have some number of them. And the first rule gives me that. I say bounds is either a single bound or it is a single bound followed by more bounds. That gives me any number of bounds. And then I have to say what a single bound is, and that's a bracket with a number followed by another bracket. So these two rules are suffice to parse any number of array bounds. Now I can do that a little bit more compactly. Instead of having repetition represented in this way, in EBNF I can say give me one or more of the bounds. In Scala, of course, I can faithfully translate that, but in Scala it's usually easier to step back and say, what did I want? I want repetition, and in that case you can just use the rep construct. Well, not quite. Rep gives me 0 or more, but with these bounds, presumably I want to have at least 1. So here's one way to get 1 or more. I can say, give me a bound, and then followed by a repetition of bounds. That way I get 1 or more. And then I can parse that out and say, when I get that, transform it as follows, because we have a head and a tail which may or may not be empty, and then I can put them together into a complete list by saying head followed by tail. So that, what you see here, is a way of representing the rule in Scala. As it turns out, because this situation happens so often that you want to have 1 or more and not 0 or more, some friendly soul has written a rep1 combinator that takes care of the 1 or more case automatically. So what you really would do in Scala is you would just use rep1 and say bounds is rep1 of bound. And notice now you don't have to do any more transformation, because rep1 returns a list of length at least 1 that contains whatever bounds there are in here. So having another look at def bounds, notice I didn't even specify a type. What is the return type for bounds? The list of what?
Type bound.
So then the next question is, what does bound return? So what does bound return? Well, hopefully not in any, because then we would get a list of any, which we don't really love. So let's see what bounds actually what bound without an S actually returns. Well, where is it? It's right here. Right, here's the function bound. I forgot to put a def before it. Just imagine there is a def. What's it return? An int, exactly, right? Because the transform here transforms the string to an int. So that's an int. Back to my original question. What is the return type of bounds? So list of int is almost correct. What is actually the return type of bounds?
Parser list of int.
Very good. It's a parser of list of int. Okay? Now here's another common situation. Look at function arguments. If I want to parse a function, and now I want to parse the arguments that are put inside. So I have an expression, a comma, an expression, a comma, and so on. And of course I have one more expression, then I have commas. So here's one way I can express that. I can say I have an identifier followed by a parenthesis, followed by an expression, and now followed by a sequence of 0 or more, comma, and expressions. Oops, there's a squiggle missing here. This again is such a common situation that there's a shortcut for it. The rep-set combinator takes the thing that is being repeated followed by the thing that separates the two. So here I can use rep-set and then the comma. Rep-set gives a list just like rep and rep1. And that list only contains the things that we're collecting, the expressions. So in this case, it would be a list of expression. It discards the commas. They're just used for parsing. So those convenience combinators are nice, and we're going to be using them frequently. So the next thing that we need to have a strategy for, when we add operators to the various languages that we're parsing, those operators will have some kind of precedence. You already know how to deal with the fact that addition and subtraction should be weaker than multiplication and division. We layer the parsing by saying an expression is a sum or difference of terms, and a term is a product or quotient of factors. And by going from expression to term to factor in this layered order, we get that multiplication binds strong. Now let's say we want to toss in another operator in here that binds even stronger. So here I'm using the caret operator for raising to a power, as one does in some programming languages. And then that should go even stronger than the multiplication. And so the way you deal with that is you add another rule just like it below the multiplication and above the thing with the whole number and the parenthesized expression. And I can never think of any good way of naming these things, so I name one of them randomly factor 1 or some such thing. And so you can see here, then I said, okay, I have a factor, and then I just call this one a factor 1. Yeah, maybe I should have called it a power or an exponent or something, but I was just lazy and did it like that. What about a weaker operation? Let's say equal, equal, and not equal. This is a Pascal style, not equal here. Then I would just put them on the top instead of on the bottom. So I would put them above the plus and minus. So now I have to say an expression is an x per 1 separated with these new operators from an expression. And then an x per 1 goes on to be a sum or a difference of terms. And again, maybe I could come up with cleverer names for that, but I didn't bother. So if you're faced with that situation, you would do the same thing. You would have to figure out where in the hierarchy do your new operators go, and you define them like that. That's maybe not the most elegant way of doing it, but it'll suffice for what we want to do in this class. The other thing with operators is when you define an operator, you have to worry about the associativity. We started with that in the last lecture, where we said that we had these left associative operators, and then the parse tree came up in the wrong direction, and then we had to transform it. Now let's look at right associative operators. So those turn out to be very easy and natural. Here I have an example. Assignment. I'm using a Pascal style assignment with a colon equal. Assignment is naturally right associative. I first need to assign the 3 to B, and then the result of that is again a 3, and then that gets assigned to A. So in this case, I don't have to worry about the grammar rule very much. I can just say that an assignment is either an identifier and a colon equal followed by an assignment, or it's an identifier colon equal an expression. So this one here is the second case. Oops. And this one here is the first case where you have identifier colon equal followed by an entire assignment. And this will now parse naturally the right way, because if we parse it, we get an identifier, a colon equal, and then an assignment, and that is the thing over here. So it works. It builds the right parse tree automatically. So for operators that bind to the left, you could think of rewriting the grammar rule in the left recursive way, but that's undesirable for us because then you get an infinite call. And oops, it says see below for remedy. I thought I fixed that. Yeah. So in the last lecture, we talked about how you deal with left associative operators. You still need to use right recursion, but then you collect all of the terms together and you use a fold. So that means now with any operator, you know how to deal with operator precedence and operator associativity. Now, most operators are, of course, left associative, plus, minus, times, and so on. Which operator do you think you might be called upon to implement that is right associative?
List cons.
Yes. So the list, the colon, the cons operator for a list is right associative, and indeed there will be a time in your life where I ask you to do that. So you will need to figure out what is the correct precedence for that operator, and then you need to make a grammar rule, which turns out to be simple because it's easy to deal with right associative operators. All right, a bit of terminology. When you parse, when you use a grammar to parse something, you start with whatever the starting rule of the grammar is. Expression, if you just want to parse expressions, or program, if you want to have a whole program. And then you will apply various productions until finally you have the entire input parsed out and you have a parse tree. Now, the question is, of course, when you're faced with alternatives, which production do you take? So if you look at, just look back at here, this grammar here, the choices are always when you have a vertical bar or when you have a question mark. So when the expr function at some point has to make it calls term, and then it has to make a choice. Does it continue? Or does it say, I had enough? And does it take the plus or the minus? So anytime that you have a choice point, there's a potential there's a potential ambiguity. Now, some parse toolkits can handle that ambiguity by picking, going down one track, seeing if it works out, and if not, then they backtrack. But that's naturally expensive. And so what we're looking for is parsers that are unambiguous, that can completely deterministically parse. And also when a parser makes the decision that, what do they have to make the decision? They have the entire rest of the string, of course, but it would be expensive to analyze the entire rest of the string for making a decision. So a parser that can make deterministic decisions by just looking at the next token is called an LL1 parser for historical reasons. So LL1 means that the parser knows what choice to make in the next step by just looking at the next token. And so that's a desirable property for parsers. And so generally we want to build grammar rules that lead to that behavior. So if we look at, for example, 3 plus 4 times 5. So we know we have to start with the expression. And so the first thing says, we must call term. So we're going to call term. Term calls So, let's look at the rule for term. Term is going to call factor, and the second rule here is not going to be applied because looking at the next token, you see that it's going to be impossible. The next token is a plus, and here this rule would only work out when there is a star and an asterisk. So it's not going to use that rule. So it's going to go down to term factor of whole number, and that's going to be parsed. Then the plus here is going to be eaten up, and then we have an expression here. And so then this thing is going to be parsed out as an expression again. So the important point is that because the way the grammar is constructed, that the choice points can always be taken care of by looking at the next token. So one of the things that you want to avoid when building these kind of deterministic grammars is left recursion. Left recursion means that a grammar function calls itself right away. So in this situation here, there's no choice that this rule can make. It's supposed to choose between calling expression and term, but there's nothing there. It would first have to call expression to see whether this plus here can guide the choice. And then you already have an infinite recursion. So in general, you want to remove this kind of ambiguity. You want to be in a situation where you restructure the grammar. And so here is a way to restructure the grammar, where we say, instead, this thing is a sum of terms. And so now I'm going to write the sum of terms a little differently. I'm going to say either it's a single term, or it's a term followed by something that I call rest. And rest always starts with a plus. And so it's a plus a term, and then more of a rest, which might be more of a plus a term. And I guess I need to say, or it's empty. I forgot about that part. So in this case here, the decision that needs to be made is once the first term is parsed, do I keep on going? And it'll keep on going if it sees more pluses, and it'll not keep on going if it doesn't see any more pluses. So we talked about this, that this works in Scala. You can program it, but the most convenient way to program it in Scala is to say, instead of eating one plus at a time, we want to have all of the plus followed by term collected together. Now I have a list of all of the terms, and once I have that, then I can use fold to put them all into one thing. So that fold trick is one that you will always end up using if you have a sequence of these operators. So there are other parsers that are not bothered by these kind of left recursive rules at all. Those parsers have a different parsing strategy than the combinator parser. They use some stacks and some other decision making, and you might learn about that when you take a course in compiler construction. For us, we are only using our one parser, and we have to live with what it can offer. Here's another common situation, that you have a grammar rule that says something can either be like what I call alpha here for the first part, followed by beta, or alpha followed by gamma, by something else. And again, in this case here, it can't be, you can't tell which of the two rules to pick by looking at the next token. The next token is going to be something that can be produced by alpha, and so it just doesn't give us the choice. So I'll give you a practical example of that. Let's look at a procedural language that has assignments and procedure calls. An assignment has the form an identifier colon equal an expression. Clear enough, right? Like x equals 9. A procedure call has the form an identifier followed by parentheses followed by comma separated expressions. And now let's say we're parsing something and where we're seeing as the next token x. And we would like to be able to make a decision with only one token look ahead. Now when we see x, then we don't know whether it's x equal colon equal 9 or whether it's a procedure called x with parentheses. Now, of course, who would ever call a procedure x, right? But you can't go by that, right? Someone could theoretically call a procedure x, or someone could call a variable println, and so you can't go by the names of it. You just have to follow the formalism. So here's how to deal with something like this, and this will happen to us in the languages that we build. We say, well, we need to consume the identifier first, and then we need to be at a point where we can make a decision. And so you make the rule for statement to say it's an identifier followed by a rest. And then we define rest on the next line as a separate non-terminal. We say a rest is either a colon equal expression or it's a parenthesis followed by expressions. Now we are deterministic because when calling rest, by looking at the next token, it's very clear whether we're going to be using this rule or whether we're going to be using that rule. If the next token is a colon equal, then the first one applies. If the next token is a parenthesis, then the second one applies. So the annoyance with that is that rest now has to kind of carry as its result two completely different things inside. That rest could either be the second half of an assignment, or it could be the parameters of a procedure call. So you need to have an object that carries that information, one or the other. So what would you call it? Assignment or maybe procedure call, some such thing. And so then you have to have these artificial looking objects. And that does actually sometimes happen with so fortunately in Scala you can often avoid this or just punt on it by using squiggle and parentheses in the way that you see here. So the Scala combinator parser will perfectly happily accept this rule here. It'll call ident, and then it'll make the decision point later here. So in general what I'm saying is that when you, it's probably not worth worrying too much about this LL1 stuff, which is pretty theoretical. I always just write the Scala rule out and the way that I think the grammar should naturally be. And then I ask myself, can this be unambiguously parsed? So if if the stat function, well, what's it going to do? Well, it's going to consume an identifier, that's fine. Or it's going to fail if there is no identifier. And then it can, by looking at the next token, it can figure out what this vertical bar is. Now, the other thing I said is that what's awkward when you have a separate rule for this rest here is that it has to carry potentially two entirely different pieces of information. In this situation, you still kind of have that issue. Oh, by the way, there's some squiggles missing here that I should put in. You still kind of have that issue. How are you now going to process this thing? Now you're going to have to put a caret, and then produce either an assignment or a function call. And so what that means is you can't throw away this symbol here because that's what's going to drive that decision. But that's okay, you can match them. So here's another thing that one needs to pay attention to when parsing. And this has nothing to do with the parser being deterministic or not. It happens. It happens in any case. So sometimes there are grammar rules that can be applied in two different ways, and both of them are correct sequences of grammar productions. Both of them are correct parsers, but as programming language designers, we only want one of them. The other one would be nonsensical. So the classic example for that is the if-else that you have in languages such as C or C++ or Java. So if you have a statement, if-else, then where does this else here belong to? Does it belong to the if over here, or does it belong to this if? The grammar rule that I gave up here can actually produce both possibilities. So let's use this grammar rule to parse this. I'm going to take off the if, the parenthesis, the C1 here, that's an expression. And then I have a statement. So in this statement is a statement, and then I can do that again, and then say the if an expression, and then the statement, else statement. That would give me this parse here, where I take the position that the child of the if is an if-else statement. Or I can use a different parsing strategy where I get the exact opposite result, where I say the if, I eat up the expression here for the C1, I then take as this statement here, I recursively call the if statement and take the if then part, and then I pop out of the recursion and get the else in that way. So there's two different ways of interpreting, of producing a valid parse. Both of them use the grammar in a correct way, and it's not clear which of them, first of all, which of them is right. That's something that the grammar can't really say. That's up to the programming language designer. So the designers of C face this issue. C++ and Java just inherited this issue in C. They faced this issue, and what did they choose? The parse tree on the left or the parse tree on the right?
The one on the left.
The one on the left. That's correct. So the designers said that an else shall group with the closest if. And they undoubtedly went through a few examples and they felt that was more natural. And I guess it is. I mean, we rarely run into this problem. Although when I teach CS1, every once in a while there's a student who just manages to do it the exact wrong way. And of course, for them it's logical, and so it's a bit of a problem. So, but that was the rule, and so we need to deal with that rule when we build a grammar. We need to produce a grammar that produces that parse tree. Just as an aside, there are other programming languages that didn't want to go down this particular rat hole, that made different decisions on how to write down an if-else. In Algol 60, a language that was an improvement not only over its predecessors, but also many of its successors. Algol 60 had the statement written as if C1, then something, else something, and then an end. And that little keyword end made it so that if you omitted the else, it was clear which part you omitted it from. You'll see in some shell languages where instead of using an end, they write the keyword backwards. So it'll be an if, and then at the end of it will be an fi. The same thing, they use that consistently, like a do might have an OD for the end of it. And so having these matching begin and end statements is a good idea, because then it removes certain ambiguities like that. All right. Now, the other thing that is a useful exercise is a useful skill is to be able to read grammars. So it very often happens that you'll get some kind of a spec document that describes some syntactical structure using a variant of the BNF notation. And we'll go through one of those in the lab just, so you can see one in the wild. So whenever someone gives you a grammar, then unfortunately the notation vary a little bit, and you have to figure out which particular variant do they use. You need to figure out which ones are the terminals and which ones are the non-terminals. What we've always done is we say the non-terminals, they don't have any delimiters around them, and the terminals, we put them in quotes. But that's not always done. So it's common to put the non-terminals with some delimiter, and so the angle bracket is very common. So you see angle bracket expert, that would be a non-terminal. And then the terminals, here the plus and minus, then they would just be written as themselves without any quotes. The disadvantage of this notation is then you also have to know what are the meta symbols. like the vertical bar, clearly doesn't mean a vertical bar literally. It means an alternative. And so then there has to be some rule for saying, well, what exactly are meta symbols? Like this is plus here. Does that mean a literal plus, or does that mean repetition of one or more? And every dialect of BNF is a little bit different, and you have to figure out exactly what they use. Another variant that you often see is, instead of using the question mark and the asterisk, they use square brackets for 0 or 1 and curly braces for 0 or more. So it's surprising how often one sees these things. We'll see in the lab, we'll see the XML standard that describes the structure of XML as a grammar. When you do internet protocols, like HTTP or something in the RFC, there may be a grammar that says how to make a request or how the response should be formatted, because it's a quick and effective way of specifying with complete precision what is valid and what isn't valid. All right, so in the lab, we're going to do two things. We're going to read through a grammar, namely the annotated XML specification. I assume everyone has some idea of what XML is. And so when you look at that, it has all sorts of grammar rules for specifying what tags are like and what elements are like. And you can see the colon, equal, you can see the vertical bars. And you can figure, so these, apparently they put single quotes around the terminals. So I'm asking a few questions to see if you can interpret those rules correctly. And in step 2, I'm asking you to produce a Scala parser for this if-else thing. Just copy and paste the outlines from the previous lectures, and then parse this thing. And now you will have written the parser in a particular way. And which of those kind of trees does it produce? The one on the left or the one on the right? And when you do that at first, you're going to get just a mess of squiggles, and that's probably not good enough to tell it, and then I'll tell you how to get a clearer picture out of it. So go ahead and do that, and then we'll all do it together. The previous class found it surprisingly challenging to get all the way to the second parser. So. And demo how to do the second part. So we're asked to put together a parser for this grammar here. So then let's turn this into Scala. So it's a def, it's a function. And now we need to put squiggles everywhere. Okay, now this question mark here we need to turn into an opt. Okay, now get a complaint about expr. It says recursive method definition needs return type. Okay, what's the return type? Well, first of all, it has to be parser because they all return parser. Parser of what?
Parser of
Well, the thing on the right-hand side is a string, a squiggle, a string, and so on. So surely it's not an int. So right now we're just going to say parser of any. Okay. Now again, another complaint about number, not found value number. And the reason is that in Java token parsers, this thing is called whole number. And then we have whole number. Okay, then I get a complaint here about this thing. Oh, I'm not even supposed to parse a val, right? I'm supposed to parse this string here. So parser.parse, also let me call it parser.parse all, because I want to parse all of it. That way, if for some reason I only parse, only a part of it matches, I get a better error message. So what's wrong here with the parser.boundif?
Where's Valdez?
Yeah, where is boundif, right? So what should it be?
Well, Expert is the only thing you have.
Expr is the only thing I have, so it should be parser.expr. Okay, now it'll compile. See if it runs. It runs. And, when it's my lucky day, I actually get it to show up in the terminal. Now, just as an aside, when I showed this in the previous section, it did not at all run in Eclipse, and I never did figure out why. I think it had something to do with that I was off to a bad start, and when I first did it, I forgot to put in the extends app, and then even though I later put it in, Eclipse never got over that. So what do you do if you can't get it to run in Eclipse and you only have 10 more minutes in the exam? Yeah, so you in the terminal, so go to the directory, this is lab 10, and just do Scala run. No, SBT run, just SBT run. Okay, now I have to remember to switch to Java 8, and now it'll really be SBT run. Alright, so then I get the same expression here. So now back to this expression. Now when you look at this expression, can you tell me whether the else groups were the first if or the second if? So he said the second. When I looked at it, I just lost the will to live. And I did not want to figure out, where all these squiggles go. And so that was my suggestion in the lab is, it's better to come up with a more realistic setup. So here I say, let's have two kinds of expression, an if expression and a number. And let's just produce a more realistic parse tree. I was also told to use this rule for numbers, so I don't have to hunt for that. Now that means that over here we're back to numbers and not whole numbers. Okay, and now of course we don't want this to be a parser of any. We want it to be a parser of what?
Expression.
Yeah, yes, absolutely. Because you might first of all think a parser of if expr, but that's only the first half. The second half is a number, and so that's an expression. So we need to have the common denominator. All right, so that means we need to transform this thing here into an expression. So I'm putting in my the double caret and leave some space here for my transformation function. And so we kind of want to clean this up and throw away the tokens we don't need. So we don't need these two. So let's put an arrow thing here. We don't need this one. Put an arrow here. Okay. So then what do we get? We get a number, a squiggle, case. A number, a squiggle, and an expression. And now maybe this thing is going to be an option. Maybe there's something in it, or maybe not. Let's do the easy case first. So if there's nothing in it, no squiggle. Then I'll do an if x, oops. OPT, turn my touchpad off. So it's an if x per, and we'll fill this in a minute. Or it's a case n squiggle e squiggle sum of f. Now in that case it's going to be really easy. Then it's an if x per of n comma e comma f. So in the first one I have a bit of a hard time because, yeah, I want n comma e, but what am I going to put for f? It wants three parameters. If x per gets in, there's a positive and the negative. If I had some way of having like an empty statement or something, then that would be one way I can do it. But let me do something simpler. I'm just going to make a second case class for the if expression that only has a then part, and I'll call it if x per 1. I don't want to mess with null or something because the nulls are uncommon in Scala, and I don't want to know where it might get into a null pointer exception. I guess I could have put an optional expression here for the negative part, but this is actually is going to be good for us. So there's going to be an expression 1 that doesn't have the else part. So in this case here, then I just put an expression 1 here, and I should be pretty much done. Except now I'm getting a nasty error here. It says type mismatch, found any required x per. And so when I looked at that this morning, I stared at it for a good long time, and I could not figure it out. And so then I decided to go back and see if maybe I made some silly mistake. There's always some list of things that can go wrong. You might forget to put one of these arrows, and then it still wants the string that's before or after it. The other common mistake is that we have a squiggle, and we have another squiggle, and we have another squiggle, and they should all have the same precedence, except we don't have another squiggle here. We have a less than sign here. And that has either a greater or a lesser precedence than the squiggle. I can never remember. And so the way to overcome that is to add another set of parentheses to make sure that the thing that starts with a less than is not interfering with the other squiggles. So if I put a parenthesis here and here, that's much better. The first error here went away. Now I still have an error in here. Let's see if I can find that out. It said no value found if e per, well, that's just a typo. Okay, and now I get an underline here, and it says type mismatch, found string squiggle x per, required x per. What did I do wrong? So let's see where this one comes from. This is f. F is the thing that sits inside the sum. That's the thing that sits inside the opt. The opt makes the none or sum. And here we have an else squiggle x per. So what's wrong? Yeah?
Because whatever f is else and also whatever the expression is. So it's not just like...
That's exactly right? So I have the else squiggle expression. How do I get rid of the else? Like this.
Oh, yeah.
And that is the significance of this operator. It throws away the thing that the arrow does not point to. And now all is happy. So let's run that. Okay. So now it parses. So, and now the final question is, which of the two parses is it? Does it do the C way, or does it do it just the other way? The C way says that the else groups with the closest if, and the other way would mean the else groups with the if that's furthest away. So the way you can tell is that the if x per 1, that's the one on top, that's the one that doesn't take an else part. So it has here the condition, which I just use numbers here for now, and then it has the entire if then else as its body. So that means the inner else grouped with the closest if. So it automatically parses the right way that we want, which is nice. Well, that's what this was supposed to show.